So now that you understand all the kinematics equations, where they come from, the concepts behind free fall, and everything that goes along with this unit of study, let's put it all into practice and see if we can solve a few problems, especially related to free fall. So the first problem is about a potato cannon that launches a projectile straight up into the air. The total time of flight is expressed as, 9 seconds. So the question is, how high did the potato chunk rise, and what was the speed as it came out of the barrel? So as a side note, it's pretty cheap and easy to build your own potato cannon, and as long as you're safe about it. You can learn a lot about physics by experimenting with your potato cannon. If you have a stopwatch and you shoot these straight up into the air, you can figure out if you can produce this same amount of flight time. And from that, you can determine what the muzzle speed is for the potato chunks that come out of your own homemade potato cannon. And when we get to our study of motion in 2 dimensions, it would be a great way to learn about projectile motion to experiment with the potato cannon. So I'm all for it. Okay, so if the cannon is pointed slightly differently than shown in this image, we point the barrel of the cannon vertically straight up into the air. And the explosion goes off in the ignition chamber of the cannon, and the little chunk of potato flies out of the barrel, travels up into the air, rises and comes back down. We have a question of 1, what's the initial velocity with which it came out of the barrel? Perhaps it rises a lot higher than this. And 2, how high did it rise? So all we're given is an amount of time, but we also are allowed to assume what the value of acceleration is, right? This is a problem in free fall after all. So let's make a frame of reference to go with this problem. Let's say the exit point of the barrel is the position where y equals 0. And for the sake of this one, let's say up is positive and down is negative. Okay, so at this point we want to always spend more time setting up the problem than solving the problem. So we have our diagram. Let's make a list. Delta y, t, v naught, v, and a. So delta y is a question, time is 9 seconds, initial velocity is a question, and the acceleration is acceleration due to gravity, which is equal to, let's see, is it positive? Oh, it's negative in this case, 9.8 meters per second squared, simply because we chose downward as the negative direction, and gravity always pulls in the downward direction. So while the potato chunk is rising, the acceleration is negative 9.8. While it's falling, the acceleration is negative 9.8, and even at the very top, its acceleration is negative 9.8 meters per second per second. You know, instead of looking at the total flight, let's do this. Let's highlight just the fall and forget the rise. So I'll say in pink, the potato chunk is rising, and in yellow, it's falling. So let's just do a study of the falling. Well, then in that case, the time spent isn't 9 seconds, it's 4.5 seconds. So I don't know if I pointed it out, but in the last video lecture, we made a graph of velocity versus time. Now the slope of this graph at all points was negative 9.8 meters per second per second. There's one instant at which the velocity is 0, but what I should have indicated, and I'm not sure I did, that this amount of time spent rising, t subscript r, time of rise, and this amount of time spent falling, t subscript f, well, they're equal. the rise time and the fall time are one and the same, provided that the object returns exactly to the same height that it was released from. Another thing is the initial velocity is some positive value. If it returns the exact same height, then the final velocity has the same magnitude, but just opposite in direction. So if I'm only considering the fall, just from point A to point B, from the top down to the ground, then the initial velocity is actually 0 meters per second, right? Right at the very top, velocity is equal to 0 meters per second. So if I can figure out the speed at the very end, when it returns back to the end of the barrel, then it has some downward velocity, but whatever that velocity moving downward is the same as what the initial velocity on the way up was. And so we'll have answered the question in that manner. Okay, so what equation should we use? Let's see, maybe it helps just to write out all of the kinematics equations. So delta y equals 1/2 v naught plus v times t. Final velocity is initial velocity plus acceleration times time. Here I'm using the symbol g for acceleration. Delta y is equal to v naught t plus 1/2 gt squared, or v squared equals v naught squared plus 2g delta y. Okay, so we have acceleration, and we have time, and we have initial velocity. So from that, it would be pretty easy to solve for final velocity if we use our second equation. So the final velocity is 0 plus negative 9.8 meters per second squared multiplied by 4.5 seconds. So dimensionally, seconds cancels a little bit with seconds squared, leaving us with meters per second. Grab a calculator if you want to double check my math. 4.5 multiplied by negative 9.8 gives negative 44.1 meters per second. Now, what's it mean that our answer comes out to be negative? It just means that the final velocity points downward, according to our frame of reference. And of course it does. But the answer to the question of what speed did it exit the barrel, we'd probably just answer that as positive 44.1 meters per second. Okay, so now that we've got the final velocity of negative 44.1 meters per second, all we have to solve for now is how high. So you could either use the first equation or the third equation, right? Let's go with the first equation. So delta y is equal to 1/2 times, okay, so the initial velocity is, now there's two ways we can do this. Do we want to consider how far it displaced as diagrammed here in pink while it's rising, or do we want to figure how far it displaced as indicated in yellow? Well, it doesn't really make a difference, right? So let's go with rising. So we know it starts out with positive 44.1 meters per second, reaches a velocity of 0 at the top, and then returns to the ground with a velocity of negative 44.1 meters per second. So, gosh, if we used positive 44.1 as the initial velocity and negative 44.1 as the final velocity, let's see what we'd get by applying this equation. We'd get 1/2 times positive 44.1 plus negative 44.1, and then we'd multiply all of that by 9 seconds. Takes a total of 9 seconds in the air. 4.5 seconds to rise, 4.5 seconds to fall, 9 seconds overall. But of course, all this would give 0, and we'd have a displacement of 0. But of course it's a displacement of 0. When an object returns to the same position it ended up at, then the overall displacement is 0. So that's not what we're looking for. We want the displacement from when it first leaves the barrel until it reaches the top. So do over delta y is equal to 1/2 times 44.1 meters per second plus 0. So from the bottom to the top, times, not 9 seconds, 4.5 seconds, okay? So if I'm considering these as the velocity values, then I have to put in the corresponding amount of time that it took to go between those two values, which is half of the overall flight. Seconds cancel seconds, we're going to be left with meters, so let's do the math on this one. If I multiply 44.1 times 4.5 and divide that by 2, we get a delta y equal to about 99.3 meters. Okay, let's move on to another problem. If a penny was dropped from the top of Sears Tower in Chicago, which is 442 meters tall, how fast would it be traveling just before it strikes the ground if we were to assume there's absolutely no air resistance, if it was truly in free fall? So you've got a really, really tall building. Someone stands at the top. I don't think you can actually get on the roof of Sears Tower, and I also don't think you'd be that big. Anyhow, there's a penny. Let it fall under the influence of gravity and is traveling very fast when it strikes the ground. How fast is that? So we know the initial velocity is 0, and we're given a displacement of 442 meters. So let's make a frame of reference in this case. Instead of putting 0 at the ground, how about we put the place where position is equal to 0 at the very top, where the penny was released from? And instead of saying up is positive and down is negative, how about we reverse it in this frame of reference? Let's say up is negative and down is positive. Okay, so we've got our diagram. Let's make a list: delta y, t, v naught, v, a. So let's see, delta y is, since the object is displacing in the downward direction, and downward means positive for me, then delta y is positive 442 meters. The time was not given or asked for. Since it was dropped, the initial velocity is 0. The final velocity is the question, and the acceleration is acceleration due to gravity, which is negative 9.8 meters per second squared, right? Well, sometimes, but not in this case. In this case, it's positive 9.8 because, again, positive means downward, and acceleration due to gravity is something that always pulls in the downward direction. So one of the biggest mistakes you'll make in kinematics problem solving is forgetting to put your frame of reference in the diagram, which is a surefire way to make mistakes with positive and negative signs. So if you take more time to set the problem up than you do solving the problem, you can avoid those mistakes. So let's see, what's the equation that doesn't involve time? V squared equals V initial squared plus, that was interesting, plus 2g delta y. The initial velocity is 0, so final velocity is the square root of 2g delta y. So here our final velocity is the square root of 2 times 9.8 meters per second squared times 442 meters. Look at the units. You have meters squared per second squared, but we're taking the square root. This is all good. Dimensionally, things are working out. Grab your calculator, play along at home. 2 times 9.8 times 442. Take the square root of all that, and we get about 93 meters per second. Okay, now in this case, actually, when we take the square root, I guess the answer could be positive or negative, but of course we know that it's going to hit the ground traveling downward, so we select the positive result. Let's do a third problem. We'll do 4 problems overall. So on to number 3. Your friend's standing on the top of a tall tower. Okay, back to this tall tower picture. There's your friend, and he throws a baseball straight upward into the air. The velocity he throws it with is 18 meters per second. It rises, and when it turns around and comes back down, it misses his hand and continues and falls all the way to the ground below. It takes a total of 6.3 seconds from when it leaves his hand until it hits the ground. How tall is the tower? So we'll say h equals question mark. What's the height of this tower? So let's make a list. Delta y, t, v naught, v, and a. Okay, we also need to make a frame of reference. I'll make the frame of reference the point where it leaves his hand. Now I'm also going to make an assumption in this problem. I'm going to assume the height of the person is so small in comparison to the height of the building that we can ignore it from the problem, and basically assume that the person and the top of the building all correspond at the same position, and that's where y is equal to 0. So how about we say up is negative and down is positive, just like we did in the previous example, which was different than our frame of reference in our first example. So from one problem to the next, you can change how you select your frame of reference, just as long as you stay consistent with your choice within any given problem. Well, in this case, the initial velocity would be negative 18 meters per second because it's initially pointing in the upward direction. Our acceleration is positive 9.8 meters per second squared, because acceleration always points downward, and downward is the positive direction. And don't get fooled by this one. It's not like the acceleration is negative while it's moving upward and then positive while it's coming down, or even vice versa. At all points, gravity is always pulling in the downward or positive direction. So the final velocity at impact was not given or asked for. We were asked for a vertical displacement. Well, we're asked for a height anyway, and we were given a time of 6.3 seconds. So it turns out that the delta y in the equation really does stand for displacement and not distance. So I understand that the distance traveled by the baseball is reasonably large. It travels some distance up. It travels that same distance to come back down to the level where it was released, and then even more distance onward. In the kinematics equations, the delta x and the delta y's you see strictly stand for displacement, not distance. And even though it goes some distance up and back down, the displacement in that first portion of motion really is 0, because at that point it's returned back to the place where it was released from. So from the point where it's released to the point where it hits the ground, that's the displacement in the equation, and that perfectly matches the height of the building. So you could do this problem the hard way, and you could say, well, I know at the very top for an instant in time the velocity is 0, and from that and the initial velocity of 18 meters per second, I can probably figure out what distance was traveled in interval A, and then in the next moment, in segment B, it falls back down that same distance, returns back here, and is now traveling downward at positive 18 meters per second instead of negative 18. Anyway, you see where I'm going with this one. You could break the motion up into two parts, A, B, and C. But it's not necessary. If you just use the kinematics equation that says delta y equals, let's see, we want the equation without final velocity. Oh yeah, that's delta y equals v naught t plus 1/2 gt squared. When you use this equation, this delta y is going to be the displacement. So it's a one-step problem. And in fact, in this case, we got lucky. There's no algebra to do. We're trying to solve for delta y, and the equation we chose is already expressed to solve for the variable in question. So delta y is equal to negative 18 meters per second, double check why I choose negative, times 6.3 seconds plus 1/2 of positive 9.8 meters per second squared times 6.3 seconds quantity squared. Now let's look at the units as always. These seconds get squared, so they cancel with those seconds squared. So that portion of the equation is going to give us some amount of meters. These seconds cancel with these. That also yields meters. And so overall, it's just a combination of meters. Grab a calculator. So negative 18 times 6.3 is negative 113.4, and we have to combine with that. 6.3 squared times 9.8, divide that by 2. So that combines with positive 194.5. And so our overall answer is equal to positive 81 meters. The positive means that the object displaced downward, and that downward displacement matches the height of the building. Okay, last problem. This one's even more challenging. A water balloon is dropped from the top of a 50-meter tower or apartment building at the same time that a rock is thrown upward from the base with a speed of 25 meters per second. How high above the ground are the two objects at the instant that they cross paths? There's a second question, but let's just take this one bit at a time. So here's our apartment building. Here's the ground. Let's make the water balloon blue. Okay, and then there's a rock that's thrown upward. Okay, we can make the rock brown. All right, good enough. So the water balloon is just dropped. Its initial velocity is equal to 0. And then the rock is projected upward. So its initial velocity is equal to 25 meters per second. And I have to decide whether I think of that as being positive or negative 25. So let's make a frame of reference. Now in this case it's interesting. Do we want to make the frame of reference the initial position of the water balloon or the initial position of the rock? Generally we like to make the frame of reference where our origin is at the initial position of the object, but here we're comparing two objects at once. So let's go with, either way would work, but I'll suggest we go with the ground is the place where position is equal to 0. And I'll go back to the frame of reference where I say up is positive and down is negative. So we probably should make two different lists here, right? We should make one for the balloon and one for the rock. And the quantities we want to identify are, well, let's do this. Instead of making delta y's, delta y means final position minus initial position. So let's identify both final position, initial position, time, initial velocity, final velocity, and acceleration for both the balloon and the rock. We know how tall the apartment building is. We should put that in the picture. We should take this 50 meters and include that in our diagram. Any more numbers that I'm missing? I think I've got all the key numbers in my diagram. Okay, so the balloon's initial position relative to our frame of reference is up above the frame of reference, so it's positive 25 meters, whereas the rock's initial position is 0. Oh, that should be under initial position. I've got these backwards. Okay, got that fixed. Final position, well, I don't know. That's what we're trying to find. So we'll say the final state is the moment at which the two of these are passing one another. So maybe that's up here, maybe it's down here, I don't know. Let's just take a guess at it and guess that it's right there. Okay, so how far above the ground is that point? So we're trying to figure out what's the final value. They have the same final value because they're crossing paths. Okay, time, we also don't know that one. I know the initial velocities. The initial velocity of the balloon is 0. And the initial velocity of the rock is positive 25 meters per second. Final velocity, I don't know. Acceleration, I know. The acceleration is acceleration due to gravity. And for, well, let's see. the acceleration due to gravity for the balloon. Well, the balloon travels downward, and it's going to speed up as it travels downward. So its acceleration must be positive 9.8 meters per second squared. But the rock is going to slow down as it rises, so its acceleration is negative 9.8 meters per second squared. Did you catch my mistake? Yeah, that was faulty logic. Doesn't matter whether it's slowing down or speeding up. Both objects, the balloon and the rock, are being pulled by gravity, which is a force that pulls downward, and downward is negative. So they both have an acceleration of negative 9.8 meters per second squared. Okay, well, how about this? What if I just chose the equation once again that says delta y equals v initial times time plus 1/2 gt squared? And what I really mean by that is y minus y initial equals v naught t plus 1/2 gt squared. Now I could add y initial to both sides of the equation. Yeah. So if I do it like this, I get an expression y equals y initial plus v naught t plus 1/2 gt squared. Now the question is, this is an equation that applies to the balloon, or is this an equation that applies to the rock? Well, I could apply this equation to either one of them. After all, they are both objects that have a uniform acceleration, and so that's the only condition that I need in which I can apply kinematics. So how about this? Why don't I make one exception to my rule? I usually say do as much of the work as you can algebraically and only plug numbers in as a final step. In this case, I think it might work to our advantage to plug in the numbers first. Here's what I'm going to do. Wherever it is that they cross paths, now, if they cross paths more than halfway up, then the balloon has not displaced as far as the rock has displaced. But that's all right, because notice we're no longer solving for displacement. We're not solving for delta y. We're solving for final position. And regardless of where it is that they cross, crossing implies they're both at the same position. And same implies an equal sign. So what I want to do is say the initial position of the balloon plus the initial velocity of the balloon multiplied by time plus 1/2 gt squared. That's a valid expression for finding the position of the balloon. But I could also say y initial for the rock plus initial velocity of the rock multiplied by time plus 1/2 gt squared is also a way of solving for the final position. And since they both have to be the same, I can set them equal. The same 1/2 gt squared shows up on both sides of the equation, so I can cancel it out. So now I just have the initial velocity of the balloon plus, oh, I'm sorry, my bad. The initial position of the balloon plus the initial velocity of the balloon multiplied by time has to equal the initial position of the rock plus the initial velocity of the rock multiplied by time. And so we just have to go back to our chart and fill out the numbers. The initial position of the balloon is 25 meters. Where did I get 25? Oh my goodness. No, it's not. I'm sure you caught this earlier and have been panicking ever since. That, of course, should be 50 meters. I just read the problem wrong. I circled the 50 meters here, but I saw the 25 there. Okay, I'm glad I caught my mistake. So the initial position of the balloon is 50 meters. It has an initial velocity of 0 meters per second. And the initial position of the rock is 0 meters, and it has an initial velocity of 25 meters per second. I'm going to leave the units out in this case, so I'm kind of going against my own best advice, but now we just have 50. No, I can put the units in. This is 50 meters equals 25 meters per second times t. Oh, well, that's easy. I guess that means t is equal to 2 seconds. Now, that wasn't exactly the question. The question wasn't how long will it take before they pass each other. The question was how high above the ground are they? So it takes 2 seconds before they pass. Now, I can take that 2 seconds and plug it back in to this equation to figure out what that position is. So, for example, for the rock, its final position would be equal to its initial position plus initial velocity times time plus 1/2 times negative 9.8 meters per second squared times time, 2 seconds, quantity squared. Okay, so let's see, 2 squared is 4, and I've got a 1/2, so this whole term is negative 19.6, and 19.6 from 50 gives me positive 30.4 meters. Now, if we don't get the same value for the rock, we got problems. Let's double check our work. For the rock, the final position equals the initial position plus the initial velocity multiplied by time. The time is 2 seconds. Plus 1/2 times negative 9.8 meters per second squared times 2 seconds quantity squared. So, oh yeah, well sure, 25 times 2 gives me 50, and like we just saw, all this comes out to negative 19.6, which, yeah, that's 30.4. So there it is. That's the height at which they cross paths, 30.4 meters above the ground. How far below the top of the building does the rock reach its apex? So they're 30.4 meters above the ground when they cross. That's not to say that the rock has reached a speed of 0 at that point. It may still have an upward velocity. So it continues. Does the rock reach the height of the apartment building? Or does it stop somewhere above where they cross paths, but not quite at the top? I don't know. Let's figure it out. Let's see how high the rock goes. So what do we know for this rock? It has an initial velocity of 25 meters per second. It has a final velocity of 0 meters per second. If the question is asking how high does it rise, well, as the rock is rising, if it's still rising, it still has a positive velocity. As soon as its velocity for an instant reaches 0, then we know it's at its greatest height. Okay, the acceleration is negative 9.8 meters per second squared, and if we can find out how far it displaced in doing so, we know how high above the ground it reaches its apex. There's the question. We don't have to know anything about time to do this one. We just need an equation that says v squared equals v naught squared plus 2g delta y. The initial velocity, in this case, the final velocity is the 0. So we have delta y is equal to negative v naught squared over 2g. Now you might think this is a problem, but the negatives will cancel out, right? This is going to be negative 25 squared divided by 2 times negative 9.8, so the negatives cancel. Hey, grab a calculator, see what you get. 25 squared divided by 19.6 gives 31.9. Ooh, so the rock had almost reached its highest point when it crossed paths with the water balloon, but it still had a little bit higher to go before it stops and turns around. Okay, the last part of this question, how long after the water balloon hits the ground will the rock return to the ground? So I'm not going to completely solve this. I'll leave this for you, but make it a two-part solution. In other words, if you could just figure out if the problem was simply a water balloon is dropped from a height of 50 meters, how long does it take until it hits the ground? We'll call that T subscript B, the time for the balloon to reach the ground. That would be a pretty straightforward and fairly easy question to answer. And then, how about a separate question? A rock is thrown upward with a speed of 25 meters per second. It reaches its apex and turns around and comes back down. How much time does it take in total for that rock to rise and fall? And we'll call that T subscript R. And that problem by itself isn't so challenging. And so if we're just being asked, what's the difference in arrival time, you just have to subtract the two answers, and you'll have found the answer to the final part of this question. Well, thanks for staying tuned for this fairly long video segment, but I wanted to show you, now that we've reached this point, how applicable these kinematics equations are and how important it is to pay close attention to your frame of reference.